I'd like to just finish up with showing you some other combinations of metals and nonmetals to make ionic compounds. And so when I show you these examples, I'd like you to think about the structure at the atomic level that we talked about earlier in this video, and just look at the vast differences in properties of the three different types of materials: metals, nonmetals, covalent bonding, and also ionic compounds. So this first one is just a piece of iron. Nothing too unusual about it. It's not as soft, clearly, as is sodium, but you're all familiar with iron. It has that sort of a silvery color. Although this one, not so much. You can start to see it looks like it's kind of tarnished, or it's looking a little rusty. So this is a particular case where the iron metal has combined with oxygen in the air. So almost all metals will rust in their own way. As you'll see, they'll form an oxide coating because our atmosphere is, we're surrounded in an atmosphere of highly reactive oxygen molecules. So iron oxide rust, I think you can walk outside and take a look at that if you're interested, but that's an ionic compound just like any other one. But I want to show you a couple examples of iron when it can be in either the +2 or +3 charge state. So in this case, we're going to think about combining iron and chlorine. So that metal and nonmetal together. We've seen chlorine before. Let's take a look and see what happens. So depending upon the reaction conditions, we can cause iron to react with chlorine when it's in the +3 charge state. And you get this nice yellow iron 3 chloride, FeCl3. So this is an ionic compound. It's crumbly and like a salt. I can just sort of break it apart. Looks like kind of like yellow table salt, but it's a pretty nice color. If I change the conditions under which I react iron and chlorine a little bit, I can cause the iron to form the +2 state. So I've got iron 2 chloride here, and you can see that's actually quite a bit different, mainly in the color. So iron 3 tends to be kind of an orangish yellow color, like you're familiar with rust, but iron 2 is oftentimes a kind of a green color. So here are those two together, and you can just see the difference of having one extra electron on the iron ion over here in iron +2 versus iron 3, and they're completely different compounds. They react differently. They have different melting and boiling points, so they're different from each other. But again, they're an ionic compound, and they have the structure sort of similar to what you saw for sodium chloride, except we'll have iron +2 or +3 and Cl minuses. So I wanted to show you then where we get iron from when we find it in the earth. And so iron doesn't come as just the raw metal. Sometimes that's called the native form when it's found in the ground in the metal state, but iron is too reactive. And it actually reacts with a couple elements, at least it has in the Earth's history, and got deposited down. The one you're most familiar with is iron oxide, but also there's a lot of sulfur in the crust of the Earth, and so we might get things like iron sulfide or iron sulfate, where iron, sulfur, and oxygen come together. I just wanted to show you a couple examples of iron ore. An ore is the raw material that we use to extract the metal from the ground. And if you ever watch science shows, they talk about they're going to melt the ore and get the metal out. That's not completely true, because in the ore, it's an ionic compound, and we have to undergo some chemistry too. But I just want to show you the ores. This is a really common one. It's what we call hematite. Hema, like you can think of hemoglobin. Iron is the metal at the center of the hemoglobin molecule. It's what makes your blood red. In the same way that this rock, which is mostly iron oxide, it's amongst some other things, some silicates, silicon and oxygen compounds, it's rusty. This is what you find on Mars. Mars is red because all the soil, all the iron was rusted. So it's just this hard red rock. I didn't show you what sulfur looks like. Sulfur, when we extract it from the ground, is this yellow, kind of soft, crumbly material. I can break it pretty easily. but as you can see, it's just yellow sulfur. But it's very soft. It's not a metal, it's a non-metal, so they don't tend to be as hard. So iron, sulfur, and oxygen can combine in a variety of ways and give you some of the products I showed you earlier. Here's a different example. This is a sheet of zinc. You can tell it looks just like a nice shiny metal. Here we've got chlorine. If I combine zinc and chlorine to make zinc chloride, I get salt. That's this stuff, just a big lump of crumbly salt. It's a slight pinkish color, mostly white, but it's a salt just like sodium chloride or iron chloride or iron oxide. On the other hand, if we combine zinc, a couple other nonmetals, sulfur and oxygen here, we are going to get an ionic compound called zinc sulfate. And this again looks a lot like table salt. This is just a big clump of crystals. Some of these compounds, when they're exposed to moisture, they tend to clump up. They call it caking. So when you buy table salt at home, normally it'll have what's called an anti-caking agent to absorb the moisture so that the salt crystals don't start to clump together. But, you know, metal, nonmetals make ionic compound. Where do we find zinc? So when we look at raw ore, this one's not quite as exciting. This is a rock called zincite, and this is an ore that contains a lot of zinc in it. I don't know if you can see, it's got some little bit of pink color there.
That pink is the zinc oxide. It's normally colorless or white, but if impurities such as transition metals also form with the crystal, it will sometimes look pink. Normally, zinc oxide is colorless or white, like the sample I'm holding up here, which is zinc sulfate.
So we get our metals from rocks. Here's another interesting combination of iron with a nonmetal. If you take iron and combine it with sulfur, you get this really interesting material called pyrite. And it actually sort of retains some of the characteristics of the yellow sulfur. It actually looks kind of a golden color. So here's a big chunk. I don't know if you can see the kind of gold color on there. But here are some other minerals that have this stuff in there. Iron sulfide called pyrite. And in the old days in the West, when they were mining for gold, a lot of the mines that they dug into had iron pyrite, iron sulfide in it, and that gold color often fooled miners into thinking that they had found gold, and so they called this stuff fool's gold. This one is a piece of quartz which got all the little black dark speckles on there that are kind of shiny. If I can get some light to reflect off it. They are iron sulfide, fool's gold. Here's just another piece, and so there's sort of a vein running through the middle. Let's see if I can bring that closer. But that's shiny, specular stuff. That's the iron sulfide. And that was to the dismay of many a gold miner in the olden days. So here's another very common metal and an example of some of its ionic compounds. So here we've got just a piece of copper metal. Copper is one of the few metals that on occasion you can find in the ground in its native or metallic state, silver and gold being the other two most common ones. But more often than not, we find it in an ore that's some combination of nonmetals like oxygen, sulfur, and chlorine. So let's take a look and see if we have this nice metallic copper reacts with the yellowish green chlorine gas. You get copper chloride, copper plus 2 chloride. It's this beautiful green color, but it's an ionic compound. You can see it's kind of crumbly and it sort of sparkles there in the light, just like any other ionic compound. This just looks like green table salt. Another really interesting one is if you combine copper, sulfur, and oxygen, you can make copper sulfate. And copper sulfate is renowned for the beauty of its crystals, and they grow into this really nice form. They're easy to grow, and you just sort of make a saturated solution of copper sulfate and water and drop a string down in it, and as it evaporates, you get these great big crystals. But this is kind of the classic color for copper, either kind of a green or a blue color, but this is just a beautiful crystal. That is a giant single crystal of copper sulfate. Here are just some smaller ones that got crushed up. But it doesn't really look a lot like its original constituents, right? The blue crystal, and that is coming from a colorless gas, a yellow crumbly solid sulfur, and copper-colored copper metal. But there's copper in there. How do we get copper out of the ground? One of the most common copper ores is something called malachite. It's not the only one. There's a lot of copper. But here are some samples of malachite. And you can see the color of copper. Copper oxide also has kind of this color. If you look at this one right here, this sort of looks like the color on the Statue of Liberty, which was covered in copper and then over time developed what's called a patina, which is kind of copper oxide and copper sulfide. So copper oxide is a little more blackish, as you can see in some of this rock, but copper sulfide and other combinations of those give you this kind of a green color. And you can go out to eastern Oregon. I remember I was out near the Snake River one time, and I just found all sorts of these greenish rocks out there, malachite. And so just think about what has to be done in order to obtain the metal. We have to find some way to convert the ionic form of copper back into copper metal. So by the end of Chemistry 223, you'll know how to do that. It's not easy, but you'll know how to do it. So here's another great example of an ore that contains a metal in its ionic form that you might have heard of. So this ore is called Cinnabar, like cinnamon. So it's got that kind of a red cinnamon color. So most of the rock is silica and quartz. But these red sections here, they look like they're painted on, but they're actually part of the rock. And I don't know if in this one you can see the sort of looks like it's in different locations in veins. This is actually an oxide of mercury. So cinnabar is the ore from which we get mercury metal. And we think of mercury as being a liquid, but remember, mercury oxide would be an ionic solid. And it's this really nice bright red color. So what I want to show you next is just a couple last examples of metals. I told you that metals exist as crystals. And a really great metal for looking at crystals is bismuth. So bismuth, Bi. It's also got another great property that when you melt bismuth, and if it's really warm, it becomes very much more reactive to the oxygen in the air. And as it solidifies, the oxygen reacts with the bismuth and it forms what's called an oxide coating. And those oxide coatings also have, because of the way they interact with the light, they look colored, and the color will change depending upon the thickness of the film. So I don't know if you can see inside here, inside this piece of bismuth that's solidified, it was kind of hollow, but there's sort of crystalline structures, and you can see it a little bit better. Bismuth makes these really neat sort of square, spirally things when it solidifies. This is a nice one here. So you can see the sort of rainbow color. Whenever you see that sort of rainbowy color on a metal, that's because of a thin film of the oxide that forms. This is very common on iron as well. So that's bismuth. You can see a little bit more, kind of the small little crystals that are all kind of packed together, and a piece of metallic bismuth. The last one I'm going to show you here is I've melted some tin metal on a hot plate, and this is molten right now, and just wanted to show you that when a metal is hot and molten, it reacts with oxygen in the air and forms an oxide layer. So actually on top of this there's some tin oxide. I'm going to sort of scrape it away. So you see that kind of film I'm scraping? That's not goo. That is a new ionic compound, and I'm piling it up over here in the corner, this black gunk. And you can see the fresh surface is much more shiny. But as it sits, it starts to tarnish. So when you think of silver, it gets kind of a blackish tarnish on it. That's what it is, silver oxide and often silver sulfide. Mostly if you're just out in the air, it's silver oxide. But this is just a big puddle of molten metal. And if I let it sit for a minute, it'll grow another oxide coating, and I just would keep scraping that away. This is, of course, something I would want to avoid because all my tin is being converted into an ionic compound. So just like in that video where the sodium reacted with the chlorine, the same kind of electron transfer reaction is happening right before our eyes right now. So the tin metal is giving up an electron to oxygen molecules in the air and forming tin oxide. They're already forming some more. So pretty cool stuff. Chemistry. It's the science of how these transformations work. So it's very, very interesting.